All right, so now we want to talk about how do mechanical waves move through solids and through fluids. So in order to do this, I want you to watch this little video here about how does a longitudinal wave move through a solid, and then how does a transverse wave move through a solid. So if you can, watch those two videos. So put me on pause, watch them. All right, so what were you seeing? What you were seeing was individual atoms. So we had in our previous lesson, we talked about how atoms are held together by electromagnetic forces. The force of electricity is going to be holding these atoms together. But what we visualized that electromagnetic force as being was a spring. So we imagined that there was a spring that was holding those two atoms together. And then this atom was being held to this atom by a spring, and then this one was being held to this one by a spring. So all of these atoms were hooked to each other through these springs, which now they're not real springs, but we were visualizing the electromagnetic force as being a spring. And so if you imagine these things being a spring, and then we take this thing and we stretch it, this wave, as it's being transmitted through this material, you would be able to see in each individual atom moving up and down, or moving like this. So in the case of the longitudinal wave, you notice that it was doing this. In the case of the transverse wave, you notice that it was doing this. And so as these springs were vibrating, you could see the wave being transmitted through the solid. Now, what about a fluid? Okay, now we can't use this analogy with a fluid, because if we take a solid and we heat it up, then these springs, they start to break because they start vibrating harder and harder, and finally they start breaking apart if you heat it up too much. So in the case of a fluid, a wave has to be transmitted through a fluid in a different way. All right, so watch this thing from Bill Nye, the Science Guy, on sound waves. Sound travels in waves. So go ahead and watch that. Okay, now this time what we had was, it wasn't an ordered array of atoms like up here. So in the case of a fluid, now this could be either water or it could be a gas. So both cases are considered to be fluids. And so this represents individual clumps of atoms in the case of a fluid, or it represents individual air molecules in the case of a gas. And so what you saw, if you watch that video from Bill Nye, was that, let's say that a sound wave is traveling in this direction. When this thing feels the sound wave, it's going to move. And what it's going to do is it's going to run into some other atom. And then when this one gets run into, it in turn is going to run into another atom. And then this one is going to run into yet another atom. So individually, notice that the molecules are not moving very far, but the wave is. Up here, these molecules are not moving very far. Now they are vibrating up and down, or they are vibrating sideways, but that's all that they can do. But notice that the wave can be transmitted through the solid because of what the individual atoms are doing. Similarly, down here, the individual atoms are not moving very far, but the wave is being transmitted through it like that. All right, now another property of waves is going to be their speed. So how fast in meters per second are they traveling? So that's going to be the wave speed. And we have to remember that there are two different kinds of waves: electromagnetic waves and then mechanical waves. So let's talk about the mechanical waves first. The speed at which a wave travels in a mechanical wave depends on the material that it's going through. So in general, the denser the material, the faster a wave can travel through it. So look at the chart there that is on the left. So it shows what kind of material it is, and then what is the speed of sound in that material. So you're most familiar with the speed of sound in air. So it travels 340 meters per second, like 3 football fields every second. That's how fast a sound wave can travel in the air. But notice that when we go into water, the speed of sound increases. It can travel faster through water, it can travel even faster through glass, and it can travel even faster through steel. So notice as we go from air to water to these substances that the density is increasing. And so that's the reason why it's traveling faster. Look up here at the top though. Notice that in a vacuum, that's not a vacuum cleaner, so we're talking about in a vacuum, in the absence of air, the speed of sound is a big fat 0, because the sound has to be transmitted by the air molecules running into each other. So if there's no air molecules to transmit the sound, then a sound wave cannot go through a vacuum. Sound waves cannot go through outer space, for example. Now, technically speaking, yes, there is some dust in outer space that could transmit a wave, but there's really not enough. So for all intents and purposes, a sound wave will not transmit through outer space. And so there was a very interesting show that I watched once, and it was called The Expanse. And so it was a science fiction show, and there was one scene in this series where there was a soldier, 2 soldiers, and they were on some kind of a moon in which there was no atmosphere. So they could not talk to each other because there wasn't anything to transmit the sound. They didn't want to use their radio helmets because that would let the enemy know their position. So what they did was they touched their face plates together. So they took their helmet of one person and they touched it to the helmet of the other person. And then that way what would happen is as they spoke, it would cause the helmet to vibrate. And then that vibration would cause the other helmet to vibrate, and then that would turn back into a sound wave so that the other person would be able to hear it. So I thought it was a really good example of the fact that sound waves are not transmitted in a vacuum, but it was a very clever way of transmitting the sound waves. So this shows that as you increase the density, you increase the speed of a mechanical wave as it travels through it. Now also it depends on the temperature. So if you look at the picture there that is on the right, you will notice that it has a temperature going sideways, and then it has speed going up and down. And you notice as the temperature increases, the speed of sound increases in that particular kind of material. And then you also notice that it shows what would be the speed of sound in this material if there was no humidity, so 0% humidity, and then what would be the speed of sound if there was humid. And so you notice that there is a little bit of a difference in the speed of sound in humid air versus dry air. Now, that was mechanical waves. Now let's talk about light waves. So all of the different kinds of light waves, radio wave, infrared, visible light, ultraviolet, X-rays, gamma rays, So all of those different kinds of light travel at one speed. What do you think that speed is? The speed of light. So the speed of light is going to be given by its own special letter. So given by Albert Einstein. So the speed of light is going to be the letter c, and it's going to be equal to approximately 3 times 10 to the 8th meters per second. So that's how fast light can travel. So to give you an idea for how fast that is, blink your eyes. So in the time it took you to blink your eyes, you could travel from the Earth to the Moon going at light speed, or going at full impulse power if you're talking about Star Trek. I had to say it. If you want to go from Earth to the Sun going at the speed of light, it's going to take you about 8 minutes. All right? And then finally, if you wanted to travel clear across the Milky Way galaxy, that's going to take you something like 100,000 years going at the speed of light to be able to do that. So remember, all light waves travel at the speed of light. Mechanical waves, however, depend on the material. So they go at different speeds depending on the material that they're going through. Well, let's write this over here then. Speed is equal to distance divided by time. So that's the general definition for what speed is. So think about a wave. So if you've got a wave here, okay, what was the distance that a wave travels before it repeats itself? So the distance from here to here was called the wavelength. So the speed of any wave is going to be equal to its wavelength divided by, now what would be the amount of time it would take to repeat itself? Not the frequency. It was called the period, and that was given by this letter right here. So the period of a wave is given by that. That's the time it's going to take to repeat itself. So this would be the speed of any wave. However, what we can do though is we could write it like this: lambda times 1 over t, like that. And then if you recall from our previous lesson, we said that 1 over the period was called something else. It was the frequency. So finally we've got that this is equal to lambda times the frequency. So for any wave that you can think of, the speed of that wave is going to be equal to its wavelength multiplied by its frequency. And so if I'm on the exam, if I gave you 2 of those 3 letters, you then could solve it for the 3rd letter. Now, what about, though, for a light wave? So in the case of a light wave, what's its speed? It's not v, it's going to be c. So the speed of light. So for any light wave, this equation here would be the one that you would want to use. So here's an example of how you would use the equation. What is the wavelength of a 91.3, what does that M stand for? Mega. Well, it's a megahertz radio signal. So write down what you're given and what you're looking for. So the 91.3 megahertz, so hertz is a unit of frequency. So the frequency is 91.3 megahertz, but that's the wrong unit. We want to get rid of the word mega. Mega means million. A million is times 10 to the 6th power. So it's 91.3 times 10 to the 6th hertz. And then it says, what is the wavelength? So what's the symbol for wavelength? Okay, it's going to be the lambda thing. So select the formula that connects the letters. And so in this case, we're going to use this equation right here. C equals the wavelength times the frequency, or frequency times wavelength. It doesn't make any difference which one you put first. So we're going to put down the speed of light is 3 times 10 to the 8th is now equal to 91.3 times 10 to the 6th times the wavelength. So we take the 91.3 times 10 to the 6th over to the other side of the equation, solve it for lambda, and it turns out to be 3.3 meters. So that would be an example of how to use that formula. All right, let's take a break, and when we come back, we'll talk about what is intensity.